This is SIR Group 7, Section 3, modeling our own independent model. So we conjecture for this model that the model of the spread of a pyramid scheme is in a moderately sized suburb is similar to the spread of a rumor and a disease as we did previously. So for this model, we're going to look at a suburb with population 101,670. And of that population, there are 100,000 who are susceptible. Then we have 330 people who enter the town looking to recruit new people into the scheme. There are 1,670 residents in the town who have already heard about the scheme and are warned not to buy into it. And so in this model, we're going to be tracking the spread of the pyramid scheme over the course of a year. There are a couple assumptions that we make in this model that I'll go ahead and point out here. So first of all, we're assuming that the population in the town is constant over the course of an entire year, which is not accurate for the real world scenario when we have people entering and exiting the town all throughout the year. And then secondly, we assume that the proportions of productive interactions between individuals in this town, interactions that change one of the factors in our model, stays constant. Whereas in reality, this would vary with the state of the economy of the town, for example, the time of the year, and how convincing the recruited person is, as well as the relationships between people that may differ in the level of trustworthiness. And then finally, this is our schematic diagram of this model adapted to the SIR format. So on the left, we have the susceptible population, which feeds directly into the recruited population, which then feeds into the disillusioned population, people who are in the scheme and then decide to leave either on their own will or through talking to another disillusioned person.
So you can see here we have our system of equations. And like Isaac kind of already explained, in the first equation, which is the rate of change of the susceptible population, the only way that people go from susceptible to recruited is by interacting with the recruited person, and proportionality constant for those interactions is B. And then for the recruited population, you can see we have people entering the recruited population as they are recruited. And then there's two ways that they can leave, which is kind of one of the main ways that this differs from the rumor and the disease model. People can leave by coming to the senses on their own, which would be, that's what K is, the proportionality constant for people leaving that way. And then P is the proportionality constant for people leaving based on an interaction with a disillusioned person, where they come to their senses and decide to get out because of that. And then you can see the differential equation for the disillusioned population has the two ways that people get out of becoming recruited. So that is composed of people who came to their senses on their own, and also people who came to their senses by talking to a disillusioned person. And you can see here the initial population conditions. So we have, I won't read through those, but you can see Isaac already explained the significance. And then here are our proportionality constants, which are the parameters of the model. And you can see B, like I already talked about, is the proportion of interactions between susceptible and recruited people that result in a new recruitment. K is the proportionality constant for individuals who become disillusioned on their own. So that's like someone coming to the senses. And then P is the constant for proportion of interactions between recruited and disillusioned people that result in a recruited individual coming to their senses and leaving the scheme. And you can see that here's the graph when we use those parameters and initial conditions. The peak happens at day 104, and that's when the population of recruited people is about 65,000. And over the course of the entire year that our model tracks, the percentage of the total population who ever becomes infected is 92.6%. So that means that it leaves about 8% of people who are left, who once the scheme dies out, that's the only percentage of people who haven't been affected by it. And then that 8% is this about 6,000 people remaining in the susceptible population at the end of the year. So those are the people who never get roped into the scheme and are still safe after it comes through the town.
All right, excellent. So the last part of our presentation, we will discuss what happens when we change the values of these proportionality constants that Genevieve already talked about and defined. So we'll get into that now. All right, so here we can see what happens when we increase the value of B, which is the value that relates the susceptible population and the infected population. So when we increase the value of B, we're essentially increasing the chance that a susceptible person will get recruited into the pyramid scheme. I said infected earlier, I meant recruited. That's what we're doing for this presentation. So as you can see, look at these graphs here. The maximum value when you increase B increases substantially. As we can see right here, we got from 65,000, it goes all the way up to 76,000. So that's a pretty large increase there. This maximum value also occurs earlier in time. So instead of occurring at 104 days, it occurs at 78 days into the year. So when we increase K, so K relates so K doesn't relate any two populations. K is what the chance that a recruited person will leave the scheme by themselves without assistance from someone who's already disillusioned. So as we can see, when we increase the value of K, not very by a small margin, you can see that there's not a large change. So those are the top two graphs. So as you can see, there's really not really much of a change when we increase K by a very small amount, but when we increase it substantially, so we went from 0.000009 to 0.01, the difference is there. And you can see that the maximum value of recruited people is much, much smaller than it originally was. So it goes all the way down to almost 31,000 from 65,500. So that is a pretty large decrease. But when we increase it just by a little bit, you can see that the change doesn't happen very much. And that's because like K is, so it's only related to the size of the recruited population. So it's not relating to populations. And so the recruited population is the only thing that K will change. So if we change it by a small number, it's not going to change the whole graph by a lot. I don't know if that made sense, but I said it. So if we increase the value of P, so P is what relates the infected population and the, recruited population and the disillusioned population. And so it kind of has a similar effect to what K would. It just happens at a quicker scale. So as you can see, we've increased the value of P by two very small decimal places, from 0.000001 to 0.000003. And so as you can see, this greatly decreases the maximum number of recruited individuals. So this goes all the way down to 27,000 from the original value of 65,500. And you can also see that the populations flatten out a little earlier here. So instead of around 150,000, like around 125,000, or sorry, instead of around 150 days, around 125 days. And so that the susceptible population kind of flattens out around 43,500, as opposed to in the original graph where it flattened out at a much lower value. So yeah, that's what happens when we mess around with all these fun little proportionality constants. And that's our little SIR model. So I hope you enjoyed. It's pretty rad.
Yes, thank you for watching.